Hello everyone, in this video I will teach you how to solve a problem on Kaplan wheel turbine. So let us start with a question. A Kaplan turbine develops 24,647.6 kilowatt of power at an average head of 39 meter, assuming the speed ratio of 2, flow ratio of 0.6 and dia of boss equal to 0.35 times the dia of the runner and an overall efficiency of 90%. Calculate number 1 diameter, number 2 specific speed of turbine, number 3 speed. So here the problem is basically dealing with the Kaplan wheel turbine. So we need to design the turbine now. So for designing the turbine, the data that is given to you is the shaft power which is generated from the turbine is given. So which is of 24,647.6 kilowatt. So let us take SP as our shaft power which is generated from the turbine, which is of 24,647.6 kilowatt and under a head of 39 meters. So here the average head of the turbine, that is the head at which the turbine is working, that is given to you. Let us consider that as capital H, which is of 39 meter, and then the speed ratio at which the turbine is working is also given, which is of 2. And then the flow ratio of 0.6 is given. So we usually represent flow ratio with the symbol CV, which is given as 0.6, and speed ratio with the symbol phi, and that is given as 2. And apart from that, they have given you the dia of the bus is equal to 0.35 times the dia of the runner. So we represent dia of bus with the letter dB and dia of runner with the letter do. So here dB is 0.35 times of do, and the overall efficiency at which the turbine is working is also given, which is of 90%. So we represent overall efficiency with the symbol eta naught, which is equal to 90%. So this is the given data. Now with this data we had to design a Kaplan turbine. So that means we had to find the dia of the runner as well as the boss, and also at what speed the turbine is rotating or it is working, and then its specific speed. So for finding all these three, the data that is given to you is, they have given you the shaft power, head, working head, and then the flow ratio and speed ratio and also the efficiency. If the flow ratio and the velocity flow ratio as well as the speed ratio is given, so let us find the velocity at which the runner is, at which the turbine is working. So here to find the velocity of flow, we have the formula CV root under 2GH, where CV represents the flow ratio and H represents the total or the average head at which the turbine is working. So we know both the values. Let us substitute it. On substituting, we get 0.6 root under of 2 into G is 9.81 and H is 39 meters. So let us try to simplify this. On simplifying, we will be getting a value which is equal to 16.597 meter per second. So that gives you the velocity of flow of runner. So that let us find the velocity at which the runner is moving. Here to find the velocity of wheel, we have the formula U is equal to phi of 2 root G 2GH, root under 2GH, where U represents the velocity of wheel and phi represents our speed ratio. Again, H represents the average head or the total head at which the turbine is working. That is same. So now phi, the speed ratio is given as 2. So let us take the value of phi as 2, root under 2 into 9.81 into 39. So on simplifying, we will get a value of 55.323 meter per second, which represents the velocity of the wheel. Then let us make use of the overall efficiency formula now. So as the overall efficiency is given to us, let us find the discharge which is taking place from the turbine. To find that, we will be making use of the overall efficiency formula. So we know that overall efficiency is the ratio between the shaft power to its working power. So the shaft power of the turbine is given in the question, which is of 24,647.6, which is in terms of kilowatt. Let us keep it in terms of watt by multiplying the value with 1000. Then divided by working power. To find the working power, we have the formula rho g into QH, where Q represents the total discharge from the turbine and H represents the head against the turbine, or head under which the turbine is working. So now here we know the value of eta naught, we know SP, we know rho G as well as H. Let us find the value of Q in this case. So now let us substitute the value of eta H, that is given as 90%. So let us convert that in terms of decimal by dividing 90 with 100, which is equal to shaft power. You need to keep it always in terms of watt itself. Hence you multiply, if your value, that is given value, is in kilowatt, then you always have to multiply that in terms of 1000 to convert that in terms of watt. Then that divided by rho. Rho represents the density of water, and we know that the density of water is 1000 kg per meter cube. Keep it as 1000 into G represents the acceleration due to gravity, which is 9.81, into Q itself is unknown, let us keep Q as it is, into H is the head against the turbine, which is of 39 meter. Then on the simplifying the whole equation, we will be getting the value of Q as 71.581 meter cube per second, which gives you the total discharge which is coming from the turbine. Then, so the purpose of finding the discharge is we want to find the diameter here. So we want both the dia, that is the dia of the boss as well as the dia of the runner. For that purpose, we will have to find the discharge. So now let us write down the equation of discharge for the Kaplan turbine here. So the Kaplan turbine discharge equation is written as pi by 4 into d naught square minus dB square into V of 1, where d naught represents the dia of the runner, dB represents the dia of the bus, and V of 1 represents the velocity of flow. So we know dB in terms of d naught, that is given in the question, which is of 0.35 times of d naught. In the next step, let us equate dB with 0.35 times of d naught, and let us substitute the remaining values. So we got Q, that is 71.581 into pi by 4, keep it as it is, into d naught square is unknown, let us keep this as it is, minus of, in the place of dB, we replace dB with 0.35 times of d naught. So that gives you 0.35 d naught whole square, multiply that with V of 1, we got the value of V of 1 as 16.597 meter per second. Now let us simplify the whole equation. Let us try to simplify this. 71.581 alpha is equal to, open the bracket, shift pi divided by 4, then into, open one more bracket, alpha A. See, instead of d naught I am keeping this as A, that is the unknown here, put A square minus of minus of, again open the bracket, 0.35 into alpha A, this whole square, close the bracket, then into 16.597, then you press shift calculate. Let us solve this. 71.581 alpha, solve, then open the bracket, shift pi divided by 4, close the bracket, into, open the bracket, alpha A square minus, again open the bracket, 0.35 into alpha A, close the bracket, put square for this, again one more, close the bracket here, then multiplied by 16.597. Then you press shift calci. If you are not getting this value in a single term, and again you have to press shift calci. So if you press shift calci twice, then you will be getting the value of A as 2.5015, which represents the value of D naught. That means the dia of the runner. So this is in terms of meter. After finding the dia of runner, let us find the dia of the bus. Here we know that dB is 0.35 times of the dia of runner. So we got the value as 2.5 here. So let us substitute it as 2.5 into 0.35. You get 0.875 meter. So that completes the first part. That is the dia of both the bus as well as the runner. Let us move to the next part. Here we have to find the speed of the turbine as well as the specific speed. So we will first find the speed and then we find the specific speed of the turbine. So to find the speed of the turbine, we have the formula u is equal to pi dn by 60. So where u1 represents the velocity of the wheel here, and here in the place of d we had to substitute it as d naught, that is the dia of the runner. So n represents the speed here. So we got d naught as 2.5 and u as 55 from the second step itself, 55.323. Let us substitute it and let us try to simplify the whole equation. On simplifying, we get a value of n as 422.636 rpm, which gives you the speed of the turbine. Moving to the next step, that is the last part of the problem, it is how to find the specific speed. So to find the specific speed of the turbine, we have the formula ns is equal to n root p divided by h power 5 by 2, where ns represents the specific speed, n represents the speed of the turbine, and p represents the shaft power from the turbine, and h represents the average head or the head at which the turbine is working. So we have the shaft power as 24,647.6, which is in terms of kilowatt. Let us keep here in terms of kilowatt itself. Don't convert the value of P in terms of watt. So here we will be keeping P in terms of kilowatt itself. And then N, just now we got the value of N, that is 422.636, that divided by H. H represents the average head, which is of 39 meters. Let us take this as 39 to the power of 5 by 4. Now let us try to simplify this. 422.636 into root under 24647.6. Divide that with, open the bracket, 39, close the bracket, then within the bracket you have to enter the power. So we get a value of 680.805, which is in terms of RPM. That gives you the value of specific speed, and that completes the design of the turbine part.